Hi kids, welcome back to GraviCalc, where each week we build a new digital logic circuit using Gravitrax marble runs. We're doing this to find out how computers and other electronics work on the inside. This is the 7th lesson in the series, and today we're going to continue learning how to count like a computer. If you haven't watched the previous lessons, you'll want to watch them first because they set the foundation for this lesson. In case you're new to my channel, I'm the Masked Marble, and my videos are about all things Gravitrax. Guess what? I found my horse! Say hi-yo to Silver, kids! He's a marble steed with a need for speed. Later this summer, he's going to make his debut in a special video containing the Masked Marble origin story, so stay tuned. In the last lesson, we built a simple computer counting machine out of Gravitrax that counted to 3. Today, we're going to build a bigger computer counting machine that counts to 15. Today's track requires 2 Gravitrax starter sets to build. Build it by loading the Gravitrax app code below into the free Ravensburger Gravitrax app, then switching to manual mode to get the build instructions. When you build your track, if you want, you can replace the launch pad with an angled green catcher insert. Then you can just drop each marble on the catcher instead of launching each marble from the launch pad. It's up to you. Now go ahead and pause the video and build the track. Remember from the last lesson, we're using switches to represent zeros and ones. A switch pointing to the left represents a value of 0, and a switch pointing to the right represents a value of 1. To start with, all our switches should be pointing to the left, which means we start our count at 0. As we count, we are going to release 1 marble at a time in the track, and the switches will change positions to tell us the total count. As we count, we're going to leave all the marbles that have completed the track in the landing pad, unless we run out of marbles. If that happens, go ahead and reuse the marbles to keep on counting. Let's quickly review what we learned last week. We learned that people count using a base 10 number system, where each place value is 10 times the previous place value. But computers count using a base 2 number system, where each place value is 2 times the previous place value. Last week's track used the base 2 number system to count, but only the ones place and the twos place to count up to 3. Remember, a computer represents the number 1 as a 1, just like we do, but it represents the number 2 as a 1, 0, which means 1, 2, and no 1s. And it represents the number 3 as a 1, 1, which means we have 1, 2, and 1, 1, which add up to 3. This was admittedly a bit confusing because 1, 0 looks a lot like 10 to us, and 1, 1 looks a lot like 11, but I think it will be less confusing as we run today's track because you'll see how the larger place values work in the base 2 number system, which is also called the binary number system. First, let's figure out what the next few place values are in the base 2 number system. Remember, unlike the base 10 number system, where a place value is 10 times the previous place value, in the base 2 number system, place values are 2 times the previous place value. So the first place value in the base 2 number system is the ones place. The next place value is 2 times 1, or 2. That's the twos place. The next place value is 2 times 2, which is 4. So that's the fours place. The next place value is 2 times 4, or 8. The next place value is 2 times 8, or 16. The next place value is 2 times 16, which is 32. And the next one is 2 times 32, which is 64. Are you seeing the pattern now? With the binary number system, each place value is double the previous place value, not 10 times the previous place value. And because we're counting in base 2 numbers, we can only use zeros and ones as digits. In the base 10 number system, we can use any digit from 0 to 9, but once we reach 10, we must move to the next place value. But in the base 2 number system, we can only use 0 and 1, and once we reach 2, we must move to the next place value. Now let's do an exercise that should make this really clear. We're going to run our marbles on today's GraviCalc computer counter, and look at how the digits change in each of the place values as we count. Before we start running marbles on the track, take a quick look around the track. Along the bottom there are 4 switches. These represent the first 4 place values. Above each switch, there is a number built out of Gravitrax tiles. Moving from right to left, we see the numbers 1, 2, 4, and 8. This means that the switches below those numbers are the 1's place, the 2's place, the 4's place, and the 8's place. This gives us a 4-digit number in the binary number system, and 4 digits in the base 2 number system can count up to 15. So let's run the track. Make sure your 4 switches read 0, 0, 0, 0 by all pointing to the left. Now go ahead and run your first marble. The 4 switches should now read 0, 0, 0, 1. This means we have no 8s, no 4s, no 2s, and 1, 1 for a total of 1. Now run your second marble. The 4 switches now read 0, 0, 1, 0. We have no 8s, no 4s, 1, 2, and no 1s. So the total is 2. Now run your third marble. The 4 switches now read 0, 0, 1, 1. We have no 8s, no 4s, 1, 2, and 1, 1. So 2 plus 1 is 3. Now run your fourth marble. The 4 switches read 0, 1, 0, 0. We have no 8s, 1 4, no 2s, and no 1s. So the total is 4. Now run your fifth marble. The 4 switches read 0, 1, 0, 1. We have no 8s, 1 4, no 2s, and 1 1. 4 plus 1 is 5. Now run your sixth marble. The 4 switches read 0, 1, 1, 0. We have no 8s, 1 4, 1 2, and no 1s. And 4 plus 2 is 6. Now run your seventh marble. The 4 switches now read 0, 1, 1, 1. We have no 8s, 1 4, 1 2, and 1 1. 4 plus 2 plus 1 is 7. Notice something here. The first 3 place values are now all full. They all have a 1 in them. So watch what happens next. Now run your eighth marble. The 4 switches now read 1, 0, 0, 0. Do you see how since the first 3 place values were full, the count had to carry over to the 4th place value and reset the first 3 place values to 0? Just like in the base 10 number system when we add 1 to 999 and it becomes 1000, here in the base 2 number system, once a place value is filled, the 1 carries over to the next place value and resets the previous place values to 0. So now we have 1 8, no 4s, no 2s, and no 1s. So the total is 8. Now run your ninth marble. The 4 switches read 1, 0, 0, 1. We have 1 8, no 4s, no 2s, and 1 1. 8 plus 1 is 9. Now run your 10th marble. The 4 switches read 1, 0, 1, 0. We have 1 8, no 4s, 1, 2, and no ones. 8 plus 2 is 10. Now run your 11th marble. The 4 switches read 1, 0, 1, 1. We have 1, 8, no 4s, 1, 2, and 1, 1. 8 plus 2 plus 1 is 11. Now run your 12th marble. The 4 switches read 1, 1, 0, 0. We have 1, 8, 1, 4, no 2s, and no 1s. 8 plus 4 is 12. Now run your 13th marble. The 4 switches read 1, 1, 0, 1. We have 1, 8, 1, 4, no 2s, and 1, 1. 8 plus 4 plus 1 is 13. Now run your 14th marble. The 4 switches read 1, 1, 1, 0. We have 1, 8, 1, 4, 1, 2, and no 1s. 8 plus 4 plus 2 is 14. Now run your 15th marble. The 4 switches now read 1, 1, 1, 1. They are all full. We have 1, 8, 1, 4, 1, 2, and 1, 1. 8 plus 4 plus 2 plus 1 is 15. So the pattern should be making sense now. Notice that since we're adding one marble at a time, the ones place always toggles back and forth as we count. 1, 0, 1, 0, 1, 0, 1, 0. And when it's a 0, the one that we're adding can fit in the ones place, and it turns the 0 to a 1. But when the ones place is a 1, the one that we're adding cannot fit in the ones place. And so that digit has to carry a 1 to the next higher place value. But suppose that next place value is already full. Then it has to carry a 1 to the next higher place value. The 1 keeps cascading up to higher place values until it finds a higher place value that is 0. As it moves up, it resets all the full place values behind it to 0. In computers, each of these place values that can hold a 1 or a 0 is called a bit, B-I-T. In our GraviCalc computer counting track, each switch is a bit that can hold a single value of 0 or 1. You have probably heard the words bits and bytes. A byte is a number made up of 8 bits. That would be like having a Gravitrax marble counter with 8 switches instead of 4. Now that we have counted to 15, we have all 4 bits of our computer full. What would have to happen to count higher? Well, a 1 would have to carry over to the next place value, which is the 16's place. In digital logic adding circuits, we call this a carry bit or a carry signal. The carry bit carries the overflowing 1 from an adding circuit in one place value to the adding circuit in the next place value. We'll be using a carry bit in the following lessons, in which we build Gravitrax adding computers. But for now, let's run a 16th marble through our circuit and see what happens. The carry bit ends up in the landing pad on the left, which is our carry bit. If we had replaced this landing pad with another place value switch, that switch would now read 1. And notice how all the previous switches reset to 0. This would give us a binary number of 1, 0, 0, 0, 0, which is 16. No 8s, no 4s, no 2s, and no 1s, just 116. You probably noticed as we were counting that it's really simple to convert a base 2 number to base 10. We simply add up the values of each of the bits according to their place values. So say we have the binary number 1001. How do we figure out what base 10 number that is? we just add up the values of the place values that have a 1 in them. The binary number 1001 has a 1 in the 8's place and a 1 in the 1's place. And 8 plus 1 is 9. So 1001 is the binary number for 9. That's not so hard, is it? How can we remember what each place value is? Well, remember the base 2 number system place values are all multiples of 2, just as the base 10 number system place values are multiples of 10. The first place value is always 1, and after that we just multiply the current place value by the base number to get the next place value. Before we wrap up today's lesson, let's think about this week's track compared to last week's track. Last week's track used 2 switches to hold 2 bits of information, but could only count to 3. This week's track used 2 more switches to hold 4 bits of information and could count to 15. How high could our track count if we added 2 more switches for a total of 6 bits of information? Well, remember how the base 2 system has place values that are multiples of 2? That means that each new place value you add, the binary number you can count more than doubles. With 1 bit you can count to 1, with 2 bits you can count to 3, with 3 bits you can count to 7, with 4 bits you can count to 15, with 5 bits you can count to 31, with 6 bits you can count to 63, with 7 bits you can count to 127, and with 8 bits, which is a byte, you can count to 255. That's right, the binary number 11111111 is 255. Next week, we'll build a Gravitrax adding computer. Since computers use binary numbers, the adding computer will add 2 binary numbers and give the result as a binary number. So that will be a lot of fun. Now here's a bonus lesson for the older kids. If we want to get really large place values in the binary number system, we can represent place values using exponential notation, which is really just a shorthand way of writing numbers that are multiplied by themselves a repeated number of times. An exponent is when we write a small number to the upper right of another regular-sized number. And all it means is that we multiply 1 by the regular-sized number, the number of times shown in the exponent. For example, 2 to the 3rd power, which can also be read as 2 to the power of 3, is 1 times 3 2's, or 1 times 2 times 2 times 2, which is 8. And 10 to the power of 4 is 1 times 4 tens, or 1 times 10 times 10 times 10 times 10, which is 10,000. Well, did you know that the place values in the base 2 number system are simply a series of powers of 2? The first place value is 2 to the power of 0, which is 1 multiplied by no 2's, or just 1. The second place value is 2 to the power of 1, which is 1 multiplied by 1 2, or 1 times 2, which is 2. The third place value is 2 to the power of 2, which is 1 multiplied by 2 2's, or 1 times 2 times 2, which is 4. The fourth place value is 2 to the power of 3, which is 1 multiplied by 3 2's, or 1 times 2 times 2 times 2, which is 8. So a shorthand way to write the value of any place value is to start counting with 0 at the first place value, count to the place value you're trying to find the value of, and write 2 to that count as the exponent. If you count place values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then that place value is 2 to the 9th power, which you can solve on a calculator. It's 512. In fact, you'll find this works for any base number system. Let's say we have a base 16 number system, also known as the hexadecimal system. What is the value of the 5th place value? Well, we count 5 place values starting with 0, so we count 0, 1, 2, 3, 4. So the answer is 16 to the 4th power. The 5th place value in the hexadecimal number system is 16 to the 4th power, which is 65,536. A computer can figure that out for you. Obviously, the more digits we can count in a single place value before moving on to the next place value, the higher we can count with fewer digits. And just so you know, the digits in the hexadecimal system are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's 16 digits. Have fun exploring different base number systems, but keep in mind that computers use the simplest base number system available, which is the base 2 number system. There is no base 1 number system because a base 1 number system would only have one digit, which would be a 0. If there was a base 1 number system, a 1 would not fit in the ones place, and every time you tried to put a 1 in the ones place, it would carry to the next place, and then to the next place, and then to the next place, and so on, to infinity, since a 1 could not fit in any of the place values. But actually, since a 1 would not even exist in a base 1 number system, the only number you could ever write would be a 0, which is pretty useless for counting. But hey, at least you'd get an A on all your math tests. Okay, student, good morning.
Good morning.
We are going to have your oral test on the base 1 number system. Today, I will ask you questions of increasing difficulty, and you will tell me the answers. Are you ready?
Yes.
What is this number?
0.
What is 0 times 0?
0.
What comes after 0?
0.
What is 0 minus 0?
0.
What is 0 plus 0?
0.
How many monkeys are jumping on the bed?
0.
Recite the set of all real numbers.
0.
If train A leaves Boston at 0 o'clock and train B leaves Chicago at 0 o'clock, at what time will the trains meet?
0.
What is the national debt at this precise instant in time?
0.
What is the annual salary of a homeschool teacher in Tucson, Arizona?
0.
Recite your times tables.
0.
Count all the numbers.
0.
What's the inverse square polynomial root of the Fourier transformed eigenvector projection?
0.
You get an A.